Okay, so today we actually want to finish off our notes and get in preparation mode here for our test. So the last major topic we need to talk about in this matter unit is the composition of matter. Now, we've talked about matter in a lot of different ways. We've talked about how the particles are arranged in the phases. We've talked about how they change through the different phases. We've also talked about physical and chemical properties, and then we've also looked very closely at a very specific physical property, which was density. So what we need to do now is talk about this composition. So let's define, just like what we did with property, let's define what composition is. The composition is the general makeup of something, or you can also think of it as how different parts combine to make the whole. What are those parts? How do they look? How do they compare to each other? Remember that matter is anything that has volume and mass. Now we have two main categories within this composition that we're going to discuss: the pure substances and the impure substances. So the first one we're going to talk about are the pure substances. Pure substances are ones that cannot be broken down into smaller, more simple parts. So basically, there's a limit as to how far I can cut it down that will keep the original substance characteristics. Okay, so I can take it down probably to about the atomic level usually, or the molecular level, but I can't take it any smaller than that. These substances always have the same composition of matter. So no matter basically how I slice it and dice it, it will always be the same. It will look the same. The number of parts that are there will be the same, and those parts will be consistent throughout. So if I take a slice and I have 2 parts of phosphorus and 1 part of sodium, if I take another slice at the other end, it will be the same. It doesn't matter if I cut it vertically, like a slice of bread, or if I cut it horizontally, like a hamburger bun. I would still see the same composition no matter how I cut that. The same would hold true if it was, let's say, a liquid. If I took a little bit of the liquid from the top, it would be the same as I took a little bit of the liquid from the bottom. It would have the same components in it. And I couldn't take it smaller through any physical changes that we would have into something that is more simple. Our pure substances include 2 categories that we're going to discuss: the elements and the compounds. And we know that these elements and compounds are made up of atoms. And remember that those are the small particles that make up all the matter that exists within the universe. So let's go through and define exactly, in terms of composition, what an element is. This is a type of substance where all of the atoms that make it up are exactly alike. The atom, remember, is the smallest particle of a particular element that keeps all of the element's properties. So its mass, its charge, all of those things. We need all of the protons, all of the neutrons, and all of the electrons present in order for those properties to exist. Elements are going to contain only one type of atom. They will all have identical numbers of protons in them. So what are some examples of elements? You guys can just write a list, but I've also included some pictures to give you some visual reference. The first one is neon. The second one is iodine. The third is carbon, aluminum, copper, and sulfur. Neon here, this is a neon gas inside of a tube that has an electric charge applied to it. You guys are probably familiar with this. Many of the tubes, the signs that you see around are not simply neon, though, even though we call them neon signs. Neon only produces this orangey, reddish color. Other colors are produced using other gases, and I'll actually show those to you later in another unit. Or you could have a situation where the glass tubing itself is painted. The iodine in this picture, we have the crystalline iodine here, and you can actually see, maybe actually able to see if the lights are dim enough, that there's this purple plume of smoke almost looking coming off of it. That is the iodine actually sublimating. If you remember what sublimation is, it's where we go directly from a solid into a gas, and that is what that iodine is doing there. Carbon, that piece looks very much like a piece of charcoal. Could be even a magnified piece of a pencil lead because that is made from carbon, which is what graphite is. Aluminum, looks like somebody took a piece of aluminum foil there and crumpled it up in a ball. Copper, has a very distinctive color, and the little green valleys in there is what we call patina. That's where copper reacts with oxygen. And sulfur. This is sulfur in its crystalline form. It is a nice yellow color. Sulfur actually has, certain sulfur compounds have a very specific odor to them, like rotten eggs. And that, in fact, the sulfur-containing compounds are, of course, then in the yolk of the egg, which gives it that yellowish color. So you can see where that comes into play. Now, with the elements, you can see we have about 120 of them total, and they are arranged by atomic number on our periodic table. We have 3 basic groups. We have the metals, the nonmetals, and the metalloids. And we will actually talk more about those when we get to the periodic table. Basically, if you look at a periodic table, you have that very distinctive staircase kind of towards the center right of the periodic table. All of the elements to the left-hand side of that staircase are the metals, left and below. The ones to the right of the staircase are the nonmetals, and then certain ones that are touching the staircase are what we call the metalloids. And next unit, when we get into the periodic table, we'll go through those in a lot more detail. The second classification of pure substances are the compounds. This is a material that is made up of atoms of 2 or more different elements that are joined together. Now, compounds are going to have properties that are very, very different sometimes from the elements that they are made from. Examples of things that are compounds are things like sodium chloride, NaCl. I have an atom of sodium and an atom of chlorine combined, and that's table salt. You're all familiar with that. Another one that you're familiar with is carbon dioxide, where I have 1 atom of carbon and 2 atoms of oxygen that are combined. Now, compounds always have this ratio. So in other words, I could go anywhere in the universe and find a compound, or sodium chloride, and they would always have this ratio, 1 sodium and 1 chlorine. Same thing with carbon dioxide, 1 carbon and 2 oxygens. This idea that these compounds are always made the same way is what we call a fixed composition. Now, compounds are pure substances because we can't break them down by physical means. In other words, we can't boil or melt sodium chloride and separate it into sodium and chlorine. It doesn't work that way. Okay? These can only be broken down into elements or another compound, and those are through chemical changes. We can't do it simply by physically cutting them apart. We're not able to do that. Breaking a compound down could give those things different properties. Let me show you an example of that. Let's look at sodium chloride and its components. If I look at just sodium, sodium is a very unstable white solid by itself. It also reacts with water vapor in the air very explosively. You actually have to store pure sodium under oil so that it does not react with any sort of water. Chlorine by itself is a poisonous greenish gas. Now, I don't know about you, but between the sounds of those two, that's not anything I really want to mess around with. My body is mostly made up with water, so sodium could really hurt me. And chlorine, it's poisonous to us as humans in its pure form. It's not, again, something we want to mess with. But the thing is, when we combine the two of them, it produces something that is hard, it's a solid, white, okay, in crystal form, and that is perfectly safe for us to eat and to take into our bodies on things like French fries, popcorn, potato chips. I'm sure you guys can think of other things that we use salt on, sodium chloride. Okay, so this is what we're talking about in terms of the shifting in properties. By themselves, sodium and chlorine are not things that we want, but combined together, it's actually something that we have found useful to us as humans. Now, the second way we can classify matter, or based on its composition, so those two are our pure substances. Let's take a look at our impure substances. Impure substances are often referred to as mixtures. Mixtures are defined as different substances that share the same space, but they're not chemically combined. We can actually separate them by physical means. We can have mixtures of elements. For instance, stainless steel is a mixture of iron, chromium, nickel, and carbon. And we can also have things that have mixtures of compounds, like sparkling mineral water, where we have water, some mineral salts, as well as carbon dioxide in there to give it bubbles. We can also have other things that are a mixture of both elements and compounds. For instance, our atmosphere. It has elemental oxygen, elemental nitrogen, carbon dioxide, which is a compound, water vapor, which is a compound, and other gases that also exist both as elements and compounds. So mixtures can be made up of elements and compounds, but the idea here is that we can separate them physically. Because of that, mixtures, sometimes their composition is not always fixed. In other words, I can take a slice from one end or a piece from one end or a sample from one end, and it would be different than from someplace else within the mixture. Maybe, maybe not. It sometimes can be hard to predict. So because of that, the properties within a mixture can vary. The substances are not always evenly distributed. And I've got two kind of real-world examples for you of mixtures. The first one is a nut mixture. You go to the grocery store and you buy a can of mixed nuts off of the shelf, and you open it up. Usually at the top you'll find a lot of almonds, a couple of pecans, maybe those big filbert nuts. And then by the bottom, all you've got left are the peanuts. If I take a sample of that nut mixture from the top versus the bottom, I'm going to have a very different composition. The other example I have for you is pizza. If I take one slice of pizza from the same pizza pie, okay, it could potentially be very, very different in terms of the type and amount of toppings that it has versus a slice on another side of the pizza. Mixtures can be separated by physical means. In other words, we can make a mixture undergo physical changes to actually separate out the components. And these methods of separation include things like filtration, evaporation, distillation, chromatography, and magnetism. We are going to focus on two components or two methods of separation, and I'm going to kind of explain them to you in detail here. The others you do need to kind of be familiar with, but these two we're going to look at very closely. The first one we're going to look at is distillation. Distillation is when we separate a mixture based on the boiling points of the components. As we said when we talked about physical properties, boiling points are actually different from substance to substance. So if I have a mixture of liquids, I can actually separate them based on their boiling points. So for example, I can actually separate my pure water from seawater or salt water. What I do is I bring that mixture to 100 degrees Celsius and boil it. What's going to happen is the water will actually turn into steam. I can collect that steam and that will be pure water. And the stuff that makes the seawater salty will actually remain behind. They don't boil away. The only thing that boils away is the water itself. This is a setup of a distillation apparatus. Over here, the blue flame is from a Bunsen burner. So this red substance in here is our mixture of liquids. There's actually a thermometer coming down here, And this is actually stoppered up, so the gases can't escape out this way. This tubing here makes the gases make a right-hand turn and go down this angled neck here. This angled neck actually acts as a tunnel. There's a space inside for the gases to pass, but this hose here is actually connected to a cold water faucet. And what it does is it pushes the cold water up into a space. There's actually a little sleeve where this cold water goes, and it runs all the way around the tube where the gases are passing. It runs down here and then out this hose and drains into the sink. What that does is these gases are coming off of here very hot. It lowers the temperature of those gases so that they condense back into their pure form. So, for instance, if this is a mixture that we want to recover the water, we would turn it to steam. The steam would come and run down, or the steam would come down here, hit the cool surface of the glass that's been cooled by the cold water, and it would run down, and we would collect it down in here, and it would be pure water and safe to drink. The other method of separation is filtration. And filtration separates a mixture based on the size of the particles. And I'm actually going to be doing a demonstration for you tomorrow that will actually show you filtration. Okay? Some things that you are familiar with filtering are things like through a colander, through a tea bag, and a coffee filter. You know, you go and you make macaroni and cheese. You boil the pasta in a pot of water. Well, you then need to separate the pasta from the water. So you put it in a colander. The water is able to run out, but the holes aren't big enough to allow the pasta to run through, so it is kept behind. Same idea with a tea bag and a coffee filter. When you make tea or coffee, what you want is the flavoring that those leaves will give, or the grounds, but you don't really want crunchy coffee. That kind of tastes gross. So what the filter does in the machine is that it lets the water take the flavor from the coffee and then run out, and it leaves the grounds behind so that you don't end up with that in your coffee. Now, within mixtures, we can actually describe these as two different types. The first type of mixture we had is a homogeneous mixture. Now, I know you're going to laugh, but this prefix homo is going to come up not just here in chemistry, but also in biology. Okay, homo, the prefix homo means same. So basically, when we have a homogeneous mixture, it means that it has the same composition throughout. So the different particles and parts within a homogeneous mixture are evenly distributed. So it doesn't matter if I take a slice from one end or the other end, or from the top or from the bottom, I'm going to have the same composition throughout. Sometimes it is very difficult for us to tell the particles apart from each other, though, because they can be very small. It is uniform throughout, like I said before, wherever I slice, and sometimes they appear to be only one substance, but they're really not. There's more than one there. Examples of homogeneous mixtures include solutions and alloys. So let's talk very briefly here about solutions and alloys. A solution is a homogeneous mixture where we have one part that is dissolved in another part. And we will actually talk a lot about solutions when we get to water and pH, because those are solutions and acids. If I leave a solution to stand, it will not separate into layers, no matter how long I leave it standing. Light will pass, solutions cannot be filtered. The particles are so small that I can't separate them by filtration. The only way I can separate a solution is through distillation. So you may want to make a note of that. If I were to shine a light through a solution, the light beam will actually pass straight through. You would not be able to see the beam of light as it's going through the solution. Solutions contain the smallest particles of any mixture that we would ever discuss. Examples of solutions include sugar in water and windshield washer fluid. Now, solutions tend to be liquids, although they can be gases. But if we have a solution, like a solid version of a solution, that's what we call an alloy. An alloy is a substance that is solid that appears to be one, but it's actually made up of several different substances. It is a homogeneous mixture. And an example of an alloy is brass. Brass is actually a combination of copper and zinc. But because literally you have a copper atom and then a zinc atom and then another copper atom, we can't see the difference. We don't see stripes in the brass. It appears to be a single solid substance, but it's not. It's actually made up of two components. Now, the second type of mixture that we have are the heterogeneous mixtures. The prefix hetero here means different. So these types of mixtures have parts that are very noticeably different from one another. We can actually usually see these. Heterogeneous mixtures are not uniform throughout. Things like, for instance, ice cream and sand and water. For instance, with my Ben & Jerry's over here, if I take a scoop of Ben & Jerry's from the top and a scoop of Ben & Jerry's from the bottom, the chances are I'm not going to get the exact same scoop. Sand and water. If you go to the beach, for instance, and you scoop up some ocean water right in the surf line there, you will actually get some sand in there. And if you leave that bucket sit over time, eventually the sand all settles out to the bottom. So you're left with this layer of very clear water and a layer of sand down towards the bottom. So again, if I take a sample from the top, I'm going to get a very different composition than if I take a sample from the bottom. We have two types of heterogeneous mixtures that we want to talk about. The first one is a colloid. Colloid is a type of heterogeneous mixture where the particles are unevenly distributed. Now, if I take a colloid and I leave it sit, it will not separate into layers. So in that sense, it's very similar to a solution. Also, like a solution, I cannot filter it. So if I pass it through a filter, it will not separate into its components. It would just go right through like it was a single substance. If I shine a light beam through a colloid, it will scatter light. And we refer to this as the Tyndall effect. And I'll actually show you a picture of that here in a second. In terms of the particle size, we have medium-sized particles. And I only have one example written on the slide, but I'm going to give you two. One example of a colloid is milk. The other is fog. And the reason why I use fog as an example is because if you look, you can especially see it over here in the red. The flashlight source is over here, and it is shining that light beam through both of these samples. But you notice here how you can actually see the light beam as it's going through that red, whatever it is, that red sample. That's an example of the light scattering. That is the Tyndall effect. And if you think about when you are riding in a car and you're driving in fog, that's kind of how your headlights look. You have that bright source here, and it kind of shines out, but you can actually see the light as it's traveling through the air when you're in fog. The last type of heterogeneous mixture we want to talk about is a suspension. So again, that's a type of heterogeneous mixture. If I take this sample that's a suspension and I let it sit, it will separate into layers, or it will settle over time. Suspensions can be filtered. Most of the time they do scatter light, but it's not always a guarantee that they're going to. And suspensions of all three that we've talked about have the largest particles. Examples of a suspension include paint, muddy water, like that ocean water I used earlier, and ice cream. A good rule of thumb to tell if you have a suspension or not is, do you have to shake it or stir it? So other things that you're familiar with, like salad dressing at home. That's a suspension. You have to shake it in order to mix the oil component and the vinegar components in many salad dressings because they separate out over time. They are suspensions.